This is Euclid Book 10, proposition number 48, but before I present this proof, I would like to show you a visual demonstration of the definitions I covered in the previous video. Let me show you this. This is the illustration we're going to use. Okay. First, we're going to draw a rational straight line. That's AB right here. Then we're going to draw a binomial straight line. That's this right here. And then we're going to divide this line into its terms. So now you have CE and ED. Now what's this square right here? Okay. If we take the line AB and turn it into a square, that's going to be this. All four sides of this square are going to be the length of AB. What about CE right here? Same type of deal. What we're going to do is we're going to take the length of CE and we're going to make all four sides of this square equal in length to CE. We're going to repeat that process over here. We're going to take the length ED and all four sides of the square are going to be the same length ED. Now we're going to have another line down here. That's FG. And we're going to take this length and we're going to turn it into a square. Okay, so all four sides of this square are going to be the length of FG. Okay, now let me read the definition to you. Given a rational straight line and a binomial, we already know what those are, divided into its terms. I've already showed you that this binomial line has been divided into its terms. Just showed you that. Such that the square on the greater term is greater than the square on the lesser. Okay, so now we're going to say that the area inside of here is greater than the area inside of here. How much bigger is this area than this area? Well, we're going to tell you. Now, let me read it again. Given a rational straight line and a binomial, divided into its terms, such that the square on the greater term is greater than the square on the lesser by the square on a straight line commensurable in length with the greater. Okay. So, what's the square on the straight line? Well, there's the square on the straight line. This straight line is commensurable in length with CE. So FG and CE are commensurable. Then, if the greater term be commensurable in length with the rational straight line, okay, let me try that again. Then, if the greater term be commensurable in length with the rational straight line set out, so now, if this length right here is commensurable with this length right here, okay, let the whole be called a first binomial straight line. So now we're going to call this whole length right here a binomial straight line. Alright. Now, the second binomial works like this. If the lesser line, if this line right here is commensurable in length with this, then all of this, CD, the whole CD, is a second binomial. Okay? And the thing is that if this length is commensurable with this, and this length is it's not commensurable with this, if both of these lengths are incommensurable with this, okay, then CD is a third binomial straight line. Okay? Now you say, okay, now, what if this line is incommensurable in length with this? Okay, which this, by the way, is this. Okay, so this length here is now incommensurable with this. Alright, what happens then? Now, if this is incommensurable with this, but this is still commensurable with this, then this whole CD is a fourth binomial. Okay? Now, if this is incommensurable with this, but this is commensurable with this, then that's a fifth binomial. But if this line right here is incommensurable with both of these, okay, then this becomes a sixth binomial. All right. I know, that's a lot. But anyway, we have a proof. Alright. What is Euclid Book 10, proposition number 48? To find the first binomial straight line. Alright, this is how we're going to find the first binomial straight line. Okay. Let two numbers, AC and CB, be set out such that the sum of them, AB, has to BC, the ratio which a square number has to a square number, but has not to CA, the ratio which a square number has to a square number. And this is by Lemma 1 after Book 28. Alright, I'm sorry. This is Lemma 1 after Euclid Book 10, 28, which I think I covered in Euclid Book 10, 28. Okay. So, we're going to have AC and CB. We're going to add these two together. So the sum of them, now if you add AC and CB together, you get the line AB. That's what you get immediately. Alright. So, as AB is to BC, that's the first ratio. As AB is to BC, so a square number is to a square number. Alright. But AB to AC is not in a ratio with a square number to a square number. Okay? So if you had AB over AC, that would be one part of the ratio. It would not have a ratio to a square number to a square number. Let any rational straight line D be set out, and let EF be commensurable in length with D. Okay? So, the length of this line here, see the length of this line right here? It's commensurable in length with this. Okay. Therefore, EF is rational. Let it be contrived that, as the number AB is to AC, so the square on EF to the square on FG. And this is by Euclid Book 10, Porism. Sorry, Euclid Book 10, proposition number 6, Porism. Okay. So, as AB is to AC, okay, so as this whole length is to this whole length, so is the square on EF to the square on FG. Oh. Okay, slight fix in the diagram. Okay, so now we're going to make two squares. First of all, this square right here, you're going to take this line, you're going to make a square out of it. All four sides of that square is going to be the length of EF. What about FG right here? You're going to take the length of FG, you're going to make it into a square, and all four sides of that square are going to be the length of FG. That's how that one works. So, as AB is to AC, as those two lines, as this line is to this line, so is this square is to this square. That's another ratio. But AB has to AC the ratio which a number has to a number. Therefore, the square on EF also has to the square on FG the ratio which a number has to a number. So that the square on EF is commensurable with the square on FG, and this is by Euclid Book 10, proposition number 6. So the square on this line is commensurable with the square on this line. Okay. And we already know that EF is rational, so FG also is rational. And since AB has not to AC the ratio which a square number has to a square number, neither therefore has the square on EF to the square on FG the ratio which a square number has to a square number. Therefore, EF is incommensurable in length with FG. This is by Euclid Book 10, proposition number 9. So even though this square is commensurable with this square, this line is not commensurable with this. So these two lengths are incommensurable. Okay. Therefore, EF, FG are rational straight lines commensurable in square only. Therefore, EG is a binomial. This is by Euclid Book 10, proposition number 36. Okay, so now we know that this line right here is a binomial line. I say that it is also a first binomial straight line. For since as the number BA is to AC, so the square on EF is to the square on FG, which we already established. While AB is greater than AC, well, obviously the length of AB is greater in size than the length of AC. Okay. Okay. Let's go and review this. For since as the number AB is to AC, so the square on EF to the square on FG, while AB is greater than AC, therefore the square on EF is also greater than the square on FG. So the area of this square is greater than the area of this square. Okay. Let the squares on FG and H be equal to the square on EF. Okay, so if we took the square of FG here and we made another square out of H, okay, we take the length of H and we turn it into a square, like we've done with everything else. If we add those areas together, that whole area would be the same size as square on EF. Okay. Now since as BA is to AC, so is the square on EF to the square on FG, which we've already established, therefore convertendo as AB is to BC, so is the square on EF to the square on H. Okay. So as this whole length here is to this whole length here, that's first part of your ratio. Also true okay, the square on this line is to the square on this line. So as this is to this, so is this square is to this square. Okay. And this is by Euclid Book 5, proposition number 19, porism. But AB has to BC the ratio which a square number has to a square number. Therefore, the square on EF also has the square on H the ratio which a square number has to a square number. Therefore, EF is commensurable in length with H. This is by Euclid Book 10, proposition number 9. So, this length is commensurable with this. Should I go right on here? Therefore, the square on EF is greater than the square on FG by the square on a straight line commensurable with EF. Okay. So, there is this magical line floating around somewhere. And the square on that particular straight line is commensurable. Okay, so the length of that line is actually commensurable with EF. And EF and FG are rational, and EF is commensurable in length with D. So EF is commensurable in length with this. So therefore, EF is a first binomial straight line. This length right here is a first binomial straight line. That's how we found it. Alright. Thus ends the proof. I will tell you more in a future video. Stay tuned.